Hi everyone. So I apparently have to record the first 5 videos because they just got screwed up due to, well, my mic was not working probably properly. So it has been a long day. Let me start by that. And today I've been trying to basically record uh, a video for you that would sum up a whole course, or at least a significant part of a course that's given at Carnegie Mellon on computer architecture, uh, and with the aim of basically giving the people who have not studied architecture uh, the capability or the ability to understand better some of the design optimizations that I keep talking about, things such as the program counter, things such as pipelining and processor architectures, and what is the difference between an ARM processor and an Intel processor, and so on. And this is by no means meant to replace a proper architecture course. So this is rather meant to give you some experience with what concepts I keep talking about sometimes in the operating systems course, while you have not covered them in previous courses. And this is not mandatory, so you're not supposed to know this by heart. I'm not going to examine you on this. So view this rather as me trying to help you to get a full understanding of things that I say, because it's kind of good to basically know what your teacher is talking about when he talks about some of these design optimizations. Although they are not entirely needed, this understanding is not entirely needed to understand what operating systems do. So, and I will try to sum up. I mean, this video summarizes something like 10 lectures from the Carnegie Mellon course, and it's a really good course. It's given by one of the top people in that field, Onur Mutlu. Um, they have the whole course recorded on video, so you can actually watch the whole course. I would highly suggest for people who have not studied computer architecture to basically go through the lectures, and to the people who have studied computer architecture and feel that they're missing a few bits and pieces here and there, that they didn't, that they want more information, they want to broaden their skill set, to also watch the whole set of videos, which is the link over here, uh, because they will actually, these are given by one of the basically most significant researchers in this field and one of the most influential people in this field. So with this, I would like to start to basically go through what a computer architect does. And a computer architect is someone who basically tries to do what an architect does in for a building. A computer architect is someone who builds or designs, puts the blueprints for how a processor will look like, for how the whole computer organization will look like. And to do that, he or she needs to look at things from the past, to learn from the past. So if you compare this to an architect who works in building architecture, he would look at Greek architectural styles, Roman architectural style, Islamic architectural styles, and Gothic architectural, and combine these architectures, modern architecture, which is something very big in Sweden, and combine all of these to basically come up with a new building, or to design a new building. So he needs to look back and look to understand basically what previous people have done, understand the whole history of the computing, or not the whole history, but at least significant part of the history from the computing architecture field. They need to look at legacy applications, so applications that have been running for the past 10 years. They need also to understand what went wrong with previous architectures, but also what went right with previous architectures. So they need to basically accumulate this knowledge about the architecture, and also about the applications that have been running on this architecture. And this also is required in order to support old applications. So you do not want your next Intel processor to basically not support your your game that you just bought for 1,000 kroners. Okay. And then you need to look forward. So you need to have an eye to the future. You're building the next generation architecture. You're building new designs. You're trying to be not radical, but well, capture a lot of what will happen in the future. Listen to the dreamers, as they say. So, for example, before 10 years, nobody really believed that multi-core is going to be a big thing. Not 10 years. Well, I'm older than that, so 20 years. Rather, micro architectures with multiple CPUs were just from. I mean, nobody thought that they would be a big thing, but we hit some physical barriers, and we thus needed to increase our computational power by parallelizing our processors. You need to look up towards the applications, because these are your first-hand users. So if you're going to run basically web servers, you need to understand what web servers require from the underlying architecture as an application. If you are going to run molecular simulations, then you need to understand this too. If you're going to control a nuclear power plant with this, you need to understand what does a nuclear power plant need to understand. So you need to look up the stack, what is on top of that's going to run on top of this architecture. And this will help you understand the important problems and their nature. You need to look down also, because the computer architecture, he's the architect, right? He designs the building, but he does not really build the building. He's not the worker who builds the building. He's not the guy who makes the cement, for example. He's not the guy who make the concrete blocks. He needs to look at the tools that are available for him below him. So with the analogy of an architect cannot just think that, oh, I'm going to build a huge building that is all made from gold, because, well, gold is kind of expensive, right? I mean, building a whole building that is made of gold probably was tradition 10,000 years ago, but even back then it was just like stupid. Okay, so it's quite similar. I mean, what are the costs for what I'm doing circuit wise? What is the cost of building these transistors and such things? What are the future technologies? So, for example, as a computer architect, you look at things such as, okay, what would happen if quantum computing becomes a thing, where you can basically do everything that we're doing right now with electronics is not valid anymore, and you need to think about how the whole computer will work together. So, analogy to building architect. And the computing stack looks something like this. At the very bottom, you have the electrons that are in the atoms that actually run in the circuits, basically, in the wires. So you have the electrons, and this is studied in physics. So the power barrier, the frequency barriers that we're hitting, these are all physics. And this is here. Then you have the circuits, and this is electrical engineering. How do you how do you make transistors? How do you make capacitors? How do you make resistors, and so on? And this is circuit design. It's electrical engineering mostly. Then you have the logic. How do you basically get a few transistors together to form an AND or an OR function, or an adder or a subtractor or a multiplier, and these things. And this is actually studied. I think some of you have already studied it in the digital design course. Then on top of that, you have the microarchitecture, which basically dictates how do you put the adders together? Do you put 10 adders? Do you put one adder in your design? Do you need an XOR function? I mean, what do you need from the logic that you can build from the circuits to basically have a fully functional processor? On top of that, you have the instruction set, which is basically what are you going to expose to the programmer. And this is sometimes called the assembly code also. So you have things such as what are the functions that can be called in assembly. and then the operating system on top that basically manages this whole, well, everything down here is managed by the operating system and exposing it to a program, or a programming language, where you basically, well, design your program, and then you have an algorithm. You're trying to solve the traveling salesman problem. We're using heuristics to basically reduce the costs of shipping stuff within Sweden. So this is your algorithm, and your problem is basically reducing the costs of shipping stuff within Sweden. And this covers quite a large part of this covers computer science basically. So algorithms, programming and languages, operating systems, which is our topic in this course, instruction set architectures, and microarchitecture, logic circuits, electrons, and so on. So until here, until basically the microarchitecture, you're in the computer science, computer engineering realm. Below there, you're more towards the electrical engineering and physics realm. And you see that we as computer scientists or as engineers also, we like to abstract. So if there's something that is super complex, we like to have multiple levels of abstraction to basically make it easier to solve very hard problems. Because if I tell you I want you to solve the traveling salesman problem using electrons, that would be something that would be very hard to do. If I tell you solve the traveling salesman problem using circuits, it's again something that is extremely hard to do, to build a circuit that solves these things. Also, it is very rigid because you solve the traveling salesman problem using circuits, but you cannot really do a fast Fourier transform now because, well, you don't have that functionality. So you try to be more general. So through abstraction, you basically provide higher power to the higher levels. And the higher levels would only, in theory, need only to know about the interface to the lower level. So in theory, what you need to know from the runtime system, from the operating system point of view, is just the assembly language that is used beneath. But this is not the whole truth, because a lot of the optimizations that are done in the operating system are actually highly dependent on the instruction set that you're working on and on the microarchitecture, and this is partially what we're going to talk about today. But also a lot of things that you do in your programming language, for example, in threading, a lot of things done in threaded programs, and this is the reason I have this lecture now before tomorrow's lecture, is that, well, threads actually get affected by some of the optimizations done between the ISA and the microarchitecture. So these are things that you take into account when you work for performance, when you're trying to hit high performance. And then abstraction improves productivity, and this is something you know as a programmer by heart, because, well, programming in Java versus programming in C, you're probably much more efficient when it comes to programming Java compared to C. Most people are like that compared to, for example, trying to write it in assembly compared to trying to write it into binary. So, and I mean, you might not be proficient in Java, but you like Python or some other language, and that would be much easier to most people than C programming. So you want to know how a multi-core system looks like. Might have seen that before. Multi-core system, which is most of the processors we have today, you have multiple cores: core 0, core 1, core 2, core 3, and this is, by the way, an AMD from AMD Barcelona. I took it also from the lectures from Onur Mutlu. For each core, you have what is called a cache memory that is attached to each core, and this is actually the design of the AMD chip. This AMD chip, in many other cases, you would have a common cache over here and a common cache over here. You typically have an L0 and L1 cache layers that also are on the cores, and then you have here a shared L3 cache. I mean, this is the microarchitecture stuff. Okay, so you see, this is by choice, because otherwise you could have had just these two cores sharing the same memory, for example, over here, that same caching layer over here. and then you have the shared L3 cache, and then you have here what is called a DRAM memory controller, which basically controls how you fetch data from the memory, and you have the memory banks over here, and you have something to talk to the memory banks through the DRAM interface. And this is one design. I mean, processors will have very different designs when it comes to what they are optimized for, and you need to take into account things such as the heat dissipation when you're doing the microarchitecture for this. So I mean, how do you make sure that the whole processor does not heat up until it blows up? Like, for example, I mean, this can happen, and these sorts of things. How do you basically get rid of extra heat, and yeah, a few of these problems. Now, if you look at the previous figure, this one, there is a very clear bottleneck, which is basically the memory here. I mean, you go through to, I mean, if you do not have enough cache here, this is part of the memory, and the cache layer is usually a few megabytes. Sometimes it used to be even a few kilobytes. So you have very few kilobytes or a few megabytes in your cache, and you typically want to go to fetch things from memory, and all 4 cores or all 8 cores or all 16 cores would go through this bus, which basically makes it a bottleneck. And besides the RAM being a bottleneck, the RAM design, the way we build RAMs is that we use basically capacitors. And I hope you know what a capacitor is, but capacitor is basically a way to put voltage and store it somehow. Okay, so, and a 0 and a 1 would be defined by basically saying, okay, 1 is +5, and the 0, which is your binary system basically, is 0 volts or -5 volts. So a 1 would be +5 volts, and a 0 volt would be 0, a binary 0 would be either 0 volt or -5 volt, depending on, well, a few things. So you have you have capacitance over here, but you have a few million of these. So it's not just one, because every bit in your RAM has at least one capacitor. Okay, so that if you have 8 gigabytes of RAM, that's 8 billion capacitors. And capacitors have a property, physical properties, that they leak the voltage. So that basically means that, for example, if we look at this RAM cell, if this is basically one RAM bit, and the capacitor energy starts leaking, so instead of +5 and 0, where +5 is 1 and 0 is 0, you get a +2.5. You end up in a position where, well, what is +2.5? Is it a 0 that went spurious, or is it a 1 that lost voltage? So what you need to do is that you need to keep the voltage on every capacitor at a constant level, or close to the operational voltage for 5, basically, for a binary 1, which is typically +5. And to basically get away from these leaked currents, from basically the voltage that gets dropped, you basically need to have periodical restore to the charge. And this periodical restore is actually, we're talking about every less than a second you have to restore 8 billion capacitors. Okay, and that basically has a very high performance cost in your memory, because for a large chunk of your time you're just basically refueling the memory. Think of it like a car. If your car runs out of gas, you cannot drive until you refill. You put the gas inside, and while putting the gas, you cannot really run with the car, because then, well, the gas will just the gas hose will just break, right? They are actually built to break. So you're not going to go very far doing that. So you need to stop and do memory refresh, and that will have a large performance cost. And this performance cost is highly dependent on the size of the memory. The larger the size of the memory, the more dense the capacitors are, the more time you spend on doing these refreshes. So if you build a 64 gigabytes RAM, then you actually need to spend something like 50% of your time, of the time of using the RAM, just refueling. Well, if you do a 2 gigabytes RAM, if you build the banks to be 2 gigabytes, then you basically spend less than 10% on this. And this is one of the reasons that when you buy RAM, if you go to one of the not Biltema, but if you go to NetOnNet and try to find a RAM, the RAM is not one chip. You get typically 4 chips or 8 chips or something, depending on how large the RAM is, and that's basically to reduce the leaked currents from capacitance, because you don't want to build a 64 gigabytes RAM and spend 50% of your time doing nothing. So there are performance costs to RAM, and this is not really related to operating systems, but they are nice to know things, and they are nice to know so that you also know where does your performance go and why don't we build things in a different way. And you have Moore's law, which you probably have heard of, and if you have not heard of, you might need to go on Wikipedia now and read about it. It's one of these things that have been driving computer architecture for the past, roughly 40 years. Okay, let's get to the real deal. Let's basically start by talking about what is a computer. A computer can be abstracted into mostly 3 parts. You have a computing unit, you have some memory or storage, and you have communication between them. Of course you can have network, but you cannot have a computer that does not have a processor, and you cannot have a computer that does not have memory. You can have a computer without storage, or you can have one of these two, but the performance will be just crappy or wouldn't just work. You can't have it with just DRAM, because RAM is volatile memory, and you can just have volatile memory, so you need to have at least a small part of it running on BIOS or something. But in reality, these are the 3 things that you need to have a computer. You don't need the internet, you don't need a network card, you don't need graphics card, you do not need, there are billions of computers out there that do not have these things, right? For example, when we talk about the ECUs in cars, the electrical control units in cars, these are computers that run the actual navigation system of your Volvo, or of your Saab, or of your Passat. So these things, they do not require more than these 3 components. And these 3 components, the way they are designed, have a large footprint on how we build operating systems today, and also on how we build software today. So the most well-known architecture and the most popular architecture in the world is the von Neumann architecture, and there are a couple of other architectures, but the von Neumann architecture is all the computers, almost all the computers you will ever use in your life are von Neumann. You might want to read a bit about who von Neumann is. That's not for now. It's also called the stored program computer, because instructions are stored in memory. And one of the major differences between the von Neumann architecture and many of the other architectures is that von Neumann basically said, okay, we should design a computer where both the instructions that are going to run and the data that the instructions will operate on will be in the same memory. So you do not have, when you go to buy RAM for your computer, you don't tell the seller, I want 8 gigabytes of RAM for my data and 4 gigabytes of RAM for my instructions. The other architectures, you would actually go and do that, because you need 2 different memories for the different kinds of data that you operate on. But the von Neumann, no, you have both instructions and data on the same memory. And that basically simplifies the architecture a lot, because it adds complications to some parts, but it makes the architecture itself quite simple. minimalistic, if I may say. And then you basically, when you read through the memory, now you have your data, your password, and your username in your memory somewhere. But you also have the instructions that are going to basically send the password and the memory, the password and the username to Google, for example. This instruction is also somewhere in your memory. Okay, but how do you make, how does the computer basically understand that, okay, this is an instruction and this is data? The way that the von Neumann architecture do it is that, or does it, is that the interpretation is only based on control signals. It's basically based on some bits in your memory that with which you basically say, okay, this part of memory is instructions and this part of memory is data. And you don't do it as in this part of memory is instructions and this part of memory is data, but the way you typically do it is that for each program, you basically go and say, okay, this program is going to get 1 gigabytes of memory, and you assign 1 gigabytes of memory to this program, and this is operating system stuff now. And then within this 1 gigabytes of memory, you basically put the instructions on the bottom half or on the top half. There are two ways to do it. You either use the bottom half or top half to put the instructions, and then the rest of the memory that is allocated goes to basically your data. And this is the separation. You make the separation in software, not in the actual architecture. And as I was explaining right now, this has a profound implication on how you build operating systems today, because, well, you do not do any other thing, roughly. And one of the key premises is that you have one instruction processed at any time unit. So you take instruction 1 and then go to instruction 2 and then go to instruction 3 and then go to instruction 4 and so on. And you have a program counter, which is a register, and we'll talk about registers later and what they are, that basically points to where you are reading now, what instruction are you on now, and what data you should read now. And the program counter is advanced such that, so if you're on instruction 1, once you're done, you go to instruction 2, once you're done, you go to instruction 3. This is the abstract model, but as we will see, this is not what is implemented in reality.